Hello students, how are you? So here we are with the geometrical optics lecture number 6. So rapidly, if the screen is visible to you and I'm audible to you, please write it in the chat box so that we can start the lecture. Okay, just write it in the chat box if the screen is visible to you and I'm audible to you. I'm waiting for your response now. Hello Devan. Hello Swarnali. Hello Nanmoni. Yeah, okay. So we will move on to the lecture. Firstly, just a second now. Okay. So here we are with the lecture number 6, geometrical optics. Okay. Now without wasting in so much of time, let's deep dive into it. What we have to do today. Okay. So geometrical optics lecture number 6 we have. It is mistakenly write it here that lecture number 5. It is lecture number 6. Okay. So what is the aim for today? Firstly, we are going to recall some concept that we have covered in the previous lecture. Now the फिर हम real depth और apparent depth के बारे में थोड़ा पढ़ेंगे. Then TIR means total internal reflection. It is the abbreviation used for total internal reflection, TIR. And we will see the critical angle concept. And next, we are going to see some application of TIR. Okay, that is it. So recall, if we are doing recall, so in the previous lecture, we have covered laws of reflection. And in the previous lecture, we have covered about the real depth and apparent depth का normal shift and lateral shift. ठीक है. So if you just a second, I will changing the color of the pen. So for lateral shift in any glass slab. ठीक है. So एक glass slab होती है and the rays coming to it. This is going refraction. 2 times इसका refraction है. And this is going to shift from its original position. This shift is termed as the lateral shift. Okay, this shift is termed as the lateral shift. Okay, and what is the normal shift? Like if it is glass slab and rays falling normally to it, okay, one of the rays going like this, so it is having a refraction, two side refraction is there, दो टाइम रिफ्लेक्शन होगा. If you extend this ray, finally it will occur in this place, but the object is here. This object is shifted normally to this point. This shift is termed as the normal shift. ठीक है. ओके. सो नॉर्मल शिफ्ट ज्यादातर केसेस में हम इस तरह से लेते हैं. दिस इज द ग्लास स्लैब, वी सेंड द रे in this manner. ठीक है. That's how we are going to see the the normal shift. So this ray occur here. So this is the normal shift that we have. Okay. So for the lateral shift, we have learned the formula. What is lateral shift? L is equals to nothing but Ti 1 minus 1 upon mu, where mu is the refractive index of the material in which this shift is taking place. Okay. And what is the formula for the normal shift? Anyone told me? Have you learned this formula? What is the normal shift? Normal shift is nothing but is equals to thickness of the glass slab 1 minus 1 upon mu. ठीक है. So we have observed that if there are number of glass slab attached to one another, then what is the final value of lateral shift? So that can be calculated by lateral shift T1 I 1 upon 1 minus mu 1, T2 I 1 minus 1 upon mu 2, and so on. Okay. Similarly, the normal shift will be T1 1 minus 1 upon mu 1 plus T2 1 minus 1 upon mu 2 plus and so on. Okay. If you have n number of glass slab, so next time will be T3 1 minus 1 upon mu 3, and this is it. So this formula we have derived. Okay. It is good for your application purpose questions. Okay. There is a directly question that has been asked from this concept. Okay. So try to learn these formula. Okay. It will help you in solving numerical problem. Okay. And it will help you directly. Like, you do not have to derive the formula again and again. You just learn the formula and apply it directly to the question. Okay. Now, the case of real and apparent depth, I have told you about real and apparent depth. Okay. So first here we will discuss about the, like we have discussed it, this is the refractive index mu1 of medium 1. This is medium 1. This is medium 2 and having refractive index mu2. So this is the object that we have here. This ray is going in this direction. After getting refracted at the boundary, it is going in this direction. So if it is moving away from the normal, so it simply indicate that this mu1 is less than mu2. Means mu1 is rare and mu2 is denser. Okay. Because it is moving away from the normal. Got it? Okay. What is this angle? This angle will be angle of incidence. This is I. What is this angle? This angle will be R, angle of refraction. What is this angle? In any type of geometry, if you encounter a Z shape, okay, so this angle would be equals to this angle for any Z formation. Okay, so just keep this in mind. Okay. So here you can see this is a Z formation here. Like this is the Z formation. So here this angle will be I. And what is this angle? This angle is nothing but angle R. How? Because from normal this ray is making, this is the reflected ray. This ray making angle R with this. If I extend this ray, it is cutting normal at this point. So the angle by this ray making with the normal is R. So here is this angle will also be R. Got it? So now I named these point as A, B, C, and D. Okay. So we are doing all the calculation for paraxial ray, and for paraxial rays angles are very small. Okay. So I can consider sin I as I, sin R as R. Okay. And similarly, if I want to consider sin I is approximated to tan I, so it will, yeah, it will be okay for this. Okay, for paraxial ray. So all the calculation here is for the paraxial ray. So if I want to calculate, like this is where the object has been placed initially, and this is the actual depth of the object. This is the real depth represented by R, because object is actually present here. But what it appears, if there is a observer here, if there is an observer, so observer को these rays are, this ray appears to be coming from this point. So the image will be formed at this point. Or in other way, you can say, if this is a normal ray, you can consider. So after refraction, these rays are not going to meet because they are refracted, they are diverging. So they are meeting at some point earlier. So this is not the actual meeting of the ray. It is the virtual meeting. So this image will be virtual. So this position of this object will be virtual one. Okay. The apparent that appears to it, not exactly. It appears to us. Okay. In daily life also, you have must encountered these applications. Like if you drop the coin in a water glass and you just look at it, so it will appear to be just lifted to you. It is because of this apparent depth phenomena. Okay. So this length here, this BC length, I must write it as here. This BC here is D, which is apparent depth, and this BD is nothing but the real depth. Okay, got it? So here we are going to apply that for paraxial ray, paraxial rays. What will be happen that sin I is approximated to tan I, and sin R is also approximated to tan R. Got it? So if I apply the Snell's law here, what is Snell's law? Snell's law says that the multiplication of refractive index of any particular medium with the angle of incidence, sine of angle of incidence to it, it will be a constant quantity. Okay, means mu sine theta is always constant. So if I going to apply here that the mu for this is mu2 for this medium. So Snell's law, apply Snell's law. कैसे अप्लाई करते हैं? So you just have to multiply the refractive index of one medium. If I applying it for medium 2, so refractive index of medium 2 mu2 and the angle of incidence of refractive index, it is I. So sine of I is equals to refractive index of medium 1 with angle of refraction of another medium. Okay. If you just reverse the direction of ray, if you just reverse the direction, this angle would be considered the angle of incidence. Okay, so no worry about it. We have also encountered that sin I is nothing but it is approximated to tan I. So if I write this equation as mu2 tan I equals to mu1 tan R, okay, so there is no problem in it. So what will happen in our calculation in triangle ABC, if you consider in triangle ABC, if you apply tan I, it will gives you tan I. What is the ratio for tan? Tan is the ratio of perpendicular to the base. So what is perpendicular here? It is AB, and what is base? Base is BD. Okay, so AB is known to us, so we would kept it as it is. ठीक है, AB के साथ कोई छेड़खानी नहीं करनी. What is BD? BD is the real depth R. Okay, in triangle ACB, in triangle ACB, what do we have? Apply tan R to it. So tan R is nothing but AB by BC. AB by BC. Okay, what is the value of AB? We don't know. So no छेड़खान. ठीक है. What is BC? BC is nothing but the apparent depth that we have considered as D. Okay. Put these values in the equation number 1. So what do we have now? Mu2 tan I. Sorry. Put the value directly. What is tan I? Tan I is AB by real depth mu1 AB by apparent depth. Okay, so AB and AB got cancelled out. So here we have mu2 by mu1 equals to R by D. Okay, so this is the general formula for apparent depth calculation. ठीक है. Now, if you read the case number 1, so when an observer is in air, an object is in a medium of refractive index mu. It is similar like you are outside a pond and you are seeing inside the pond. ठीक है. So object means आप कोई भी fish ले लो या any kind of stone which is inside the lake or inside the pond, and you are observing it from the outside the pond. So you as a observer are present in air, is present in air, and that stone or that particular object, that whatever you have been considered, is present in the liquid of refractive index mu, or the medium we would consider at medium of refractive index mu. So how do we calculate the apparent depth then? So for that, this mu2 is nothing but, this mu2 is nothing but from where the ray is coming, from where the ray is coming. So wherever the object is, ray is coming from the object. Okay, so for very carefully, in this case, when observer in his air and object is in a medium of refractive index mu, where is the object? Object is in the medium of refractive index mu. So from where the rays appear to come, ray appear to come from the refractive index medium mu. Okay, so this mu2 is the refractive index of medium. Okay, so medium is mu where the object is placed. Just keep this in mind. This mu2 is nothing but the refractive index of that medium from where the ray is coming, and ray is coming from the object. So this refractive index is nothing but from where the object is placed. Okay, so in this case, object is placed in a in a medium of refractive index mu. So we have considered mu. So for case 1, this mu2 is considered as mu equals to divided by, what is this mu1? Mu1 is the refractive index of medium where the observer is, from where the ray is going. Okay, mu2 is the refractive index of medium जहां से रे आ रही हैं, and mu1 is the refractive index of medium जहां रे जा रही है. Okay, that's simple. So रे कहां पे जा रही है? एयर में जा रही है. Observer is in air. So what is the refractive index of air? It is 1. Now this R divided by D. So from here you can say that D is nothing but R upon mu, and mu is always greater than 1. Mu is greater than 1. So this D is less than R. Means for this case, apparent depth is less than real depth, and that is the reason when you drop a coin or any substance in a medium, in a in the liquid, like say water, you have a glass of water, you just put a coin in that, and if you try to observe it, that coin seems to be appear some uplifted position, थोड़ा उठा हुआ दिखेगा. That is the reason, because for apparent depth of that coin would appear less than the actual one. That is why if you have anyone, uh, like for everyone, you have a tank, water tank in your house. So if you just try to see the water tank, bottom of the water tank, it appears to be somehow uplifted, and this is because of this. Like the apparent depth for uh, the object is less than the real depth when observer are in air. Okay. Now the second case, if I want to consider, when observer in his air is in air and the object is in a medium of refractive index mu. This is the second case. Okay. So yeah, this is the object that we have. Object of, this is the ray incoming. This is also the ray coming from this. Okay, here the observer is. ठीक है. The ray is coming and it is getting refracted, but it appears the observer to be coming from this point. Okay, so this is the actual, this is the actual, this this length is the actual one, and this is the apparent one. Okay, so it appears like somehow greater than the real depth if observer is in the medium of mu and object is in a medium of air. Okay, so from the formula that we have derived, mu2 by mu1 equals to real over apparent. So what is this mu2? Mu2 is nothing but from the ray, from where the ray is coming. Ray is coming from the air, so we have to put the value of 1 divided by, from the mu1 is nothing but from where ray is going. So ray is going to the observer, which is present in a medium of refractive index mu. So just put the mu here, r by d. So for this you can say d is equals to mu times r, means for that d is greater than r, means जो object है it would appear somehow greater position than the actual one. Okay, so this is the simple concept, the very useful formula. Okay, now based on this concept we have another concept here, velocity of fish and bird. Okay, suppose this is the interface of water, this is water. Okay, here there is a beautiful fish, I'll try to make it as a fish. Okay, and this is a bird flying over here. Okay, now if I join them by a vertical line, okay, so concept one क्या है, when fish is observing the bird, so fish is in the medium of diffractive index mu, let's say, and bird is in air. So if I try to calculate and if you apply the knowledge of previous concept here, the object is in a rare medium, so it would appear somehow at greater distance. So bird कहीं यहाँ पे appear होगी उसे, किसे, fish को. So this is the apparent. I must say this is like fish की जो distance है water surface से, that is x, and water surface से ही bird की जो actual distance है, that is y. So for that it would appear at somehow higher place because the object is in the rare medium. ठीक है, we have learned this concept earlier. Like in this, when object is in rare medium, so this apparent depth would appear somehow greater than the real one. Okay, so that is why I have write v dash y dash here, the apparent one. So if I try to write the position of, I am representing the position of with r, position of bird with respect to fish is nothing but x plus this y dash. This is the position of bird with respect to fish. Okay, if I differentiate this term like dr bf by dt is equals to dx by dt plus dy dash by dt. Okay, for the sign convention just keep this in mind. Okay, if both the object means bird and fish are going towards the surface, ठीक है, surface के सारी की सारी distances, all the calculation would be done with respect to the surface. ठीक है, the first thing that is to be keep in mind. Now if they moving towards surface or interface, we must say, then considered to be negative. ठीक है, and moving away to the surface, so that would appear, that we will consider as positive. or it is in your hand. If you consider the if the object moving toward the surface, you have considered positive. So in the vice versa, you have to consider the another scenario, negative one. Okay. So I have considered if they are moving towards the surface, that could be negative, and if they are moving away from the surface, that is positive. So dx by dt is the change of position of fish with respect to the surface. Like if fish is not moving, then this dx by dt term will be 0. This dy dash by dt is the nothing but velocity of bird. Okay. So this dy dash by dt is nothing but what it is. Put the value of y dash. We can put it. Y dash is nothing but mu times of x. Sorry, mu times of y. Okay. From the previous case, it is mu times the real position, the real depth, and real depth here is y. So y dash is nothing but mu y. Okay. So put this value, it is 0 plus mu बाहर आ जाएगा dy dash dy by dt. Dy by dt is nothing but velocity of bird, and dr by, just a second, it is dr by dr bf by dt is equals to 0. Dx by dt is 0. It is mu times dy by dt. So rbf is the velocity of bird with respect to fish, is nothing but mu times velocity of bird measured from the surface. Okay. So this is the concept one. Although if this is the medium, not air, this is mu1, like I have to write it here. If relative refractive index is given to you, like 1 mu2, it is mu2 by mu1. Okay. It is refractive index of medium 2 with respect to 1. So this velocity of bird with respect to fish would be appear as 1 mu2 vb. Okay. And if it is moving towards the surface like this, if I consider this is the direction of velocity of bird, then this formula will become velocity of bird with respect to fish is minus of 1 mu2 velocity of bird. Okay. So this is up to you. However you have chosen the sign convention, this minus would appear from that convention also. Okay. Now the next concept is, if we are going to calculate, this is bird, okay, flying at an altitude of y again, and this is fish staying at a depth of x. Okay. Okay. Now if bird is observing the fish, so here you will say that this object is in the denser medium, so it would appear somehow lifted, somehow up. So it is x dash, the new position, it is less than the x dash is less than x. Okay. So from here, if I try to calculate the relative position of fish with respect to bird, is nothing but y plus x dash. Okay, this is the relative position, because for bird this fish would appear here, not at this point. Okay. So relative position of fish with respect to bird, y plus what is x dash? X dash is nothing but x upon mu, because it reduces mu times. Okay. In the previous case, it is increasing by mu times, so it reduces mu times. So if I differentiate this term, There's nothing left in this formula. dy by dt plus 1 upon mu times dx by dt. Okay, so this is the velocity of fish with respect to bird. It is equals to this dy by dt is the velocity of bird plus 1 upon mu. If the fish is also moving, then dx by dt would be considered as velocity of fish. Okay. And if the fish is stationary, then this vf becomes 0. Then velocity of fish with respect to bird will be the velocity of bird. Okay. And if relative refractive index is given, if relative refractive index is given like 1 mu 2, refractive index of medium 2 with respect to 1. So this velocity of fish with respect to bird is given by velocity of bird plus 1 upon 1 mu 2 vf, velocity of fish. Okay, so this is the simple concept that we have learned. If you have any doubt, you just write this in the chat box. Okay, so yeah, now we are facing the phenomena of total internal reflection. What is TIR? Okay, so firstly I will discuss some point with you. Okay, look, if this is the surface that I have, if this is a surface, okay, and refractive index is mu1 above the surface, below the surface it is mu2. Okay, if a ray is coming, this is the normal. If a ray is coming and it is getting refracted, okay, if mu2, if mu2 is less than mu1, so what will happen? What will happen? This ray, this ray move away from the normal. Okay, move away from the normal for any angle of incidence, for a particular angle of incidence. Now if I just increase this angle of incidence, this ray, just a second, if I just increase this angle of incidence, this ray will also, this angle of refraction will also increase. At some point, what will happen? I will encounter a particular angle I for which this ray completely shifted to this position, to the boundary. Okay, and it will not going into the medium. You can see here, if I just increase the eye, this ray will increase, the refractive angle is increases. If I would continuously increasing the angle I, then I somehow encounter an angle for which the ray grazes to the boundary but not enter in the medium. Okay. Further, if I increase the value of angle of incidence, what will happen? This ray will completely get reflected. Okay. There is no part of this ray which is going inside the medium. Okay. So this phenomena is termed as total internal reflection. Okay. Why it is different from reflection? Because this phenomena is taking place internally. Okay. If you increase the angle, if you do not increase the angle, the ray is getting refracted. But if you increase the angle of incidence, the ray is not going, instead of going inside to the medium, it is getting reflected. Okay. So that is why this phenomena is termed as the total internal reflection. Got it? So just a second. If I just remove this, okay. Okay. You can write you can read this definition. This is the TIR. Okay. This is water heavier than air. Okay, just a sec. Yeah, this is the incident ray at an angle theta getting refracted, moving away from the normal. But for critical angle, for some angle that I have mentioned, this ray is not going inside the medium. It is moving along the boundary, grazes to the boundary. This angle particularly called as the critical angle. Okay, so critical angle is the angle made in the denser medium for which the ray, for which the angle of refraction in rarer medium is 90 degree. You can see here this angle of refraction is 90 degree here. This is 90 degree. And if I just increase the value from theta c, means from critical angle, the complete ray got reflected. There is no part of the ray which is going inside the medium. Okay. So this surface behaves as the perfectly mirror, reflecting mirror. Got it? So this is the phenomenon of TIR, total internal reflection. Examples of TIR you can see in this. This ray is coming. Okay. This ray is coming. Okay. In this normal, it is moving towards the normal because it is entering in the glass and glass is denser. At this surface, at this point of, at this boundary, it is air outside. Okay. So this ray is having angle theta greater than theta c, for which it is getting completely reflected. TIR phenomena is taking place here. You can see in this GIF, by moving this laser, he or she is changing the angle of incidence for which, and this particular angle of refraction, this TIR phenomena is taking place. You can see in this very clearly, it is showing to you. Okay. Now, what is the critical angle? How do we calculate it? What is critical angle? Suppose this from where the ray is coming. Okay. Firstly, ray is coming from denser medium mu. Okay. And going into mu1 is equals to 1. I would consider medium 1 as, this is medium 1 as air, and this is as glass. Okay, and glass has a refractive index mu. Air has a refractive index 1. So for this is the angle of incidence somehow. Okay, I, this is R. But for this particular angle, what will be the value of this angle? If the angle of refraction is 90 degree, so this angle would be theta c, the critical angle of refraction. Okay, if I apply the Snell's law here, because Snell's law we can apply on the boundary conditions also. Okay, so by applying Snell's law, for this, theta c, okay, so mu multiply with sine of theta c equals to, what is the value of mu in air? It is 1. And what is the value of refraction angle? It is 90 degree. Got it? Now what is the value of sine 90? So sine theta c is nothing but 1 upon mu, because sine 90 is nothing but 1. Okay. So theta c, or you can write it as capital C, the angle of critical angle of incidence, is equals to sine inverse 1 upon mu. Got it? So this is the formula for critical angle that we have. Okay. If you have any kind of doubt, you want to note it down, you can also note it down, take the screenshot of it. Have any doubt, you can just ask in the chat box. Okay. Now, this is a application type of question or TIR. Okay, what is this question is? Firstly, we will understand that this is the source, light source we have. Just a second. This is the light source inside a container having liquid filled in. So this is the light source. Light source. So it is sending light to the boundary. Okay, this is a point light source. So the rays are diverging from it. Okay, I have told you about the uh, phenomena of how the ray diverge and inverge. Okay, just give me 10 seconds. Huh? Okay, okay. So sorry for the trouble. Now, a source inside the liquid I am talking about. This is the light source that we have. It is sending light in this direction and in this direction. Okay. So this would appear as a cone of light. Okay. Okay. So we have to find out the radius of this cone. What is the radius? From where इससे आगे we would not see any kind of light. ठीक है. So how is this happen? कैसे होगा ये? If this ray, the final ray, the end ray of this, I will consider that it falls on this interface at an angle equals to theta c. अगर this ray fall on this boundary at an angle greater than or equals to theta c, critical angle, then what will happen? For critical angle, there is a concept TIR that we have learned. This ray would not go to the another medium. It got reflected or moves along the boundary. So for theta c, if this ray falls on an angle of theta c, that no ray will come after that. Okay, out of the liquid. Okay, so that how we are going to calculate the value of radius over here. Okay, this is the r radius. This is normal to the surface. Okay, for this also this angle is I, which is equals to c or critical angle. Okay, if I just apply this Snell's law over here, apply Snell's law, just apply this. If this liquid has a refractive index mu and this air has a refractive index 1, so what will be the value of Snell's law over here? It is mu multiplied with sine capital C. Capital C is the angle of critical. Yeah, critical angle of incidence. Okay. You will write it as theta C also and write it as C. Mu sine C equals to 1 sine 90. Okay. So sine C here is nothing but 1 upon mu. This is the equation number 1 we have. Now, if you see in this triangle, if this I consider this point as O, this point as P, and this point as, let's say, A. So in triangle OPA, what is the value of this angle? Again, this is the formation of Z. If this angle is theta C, this angle would also be theta C or C. So in triangle OPA, OPA, if I apply, okay, now what is the value known to us? The values are known to us is this only, the radius, or we can consider this depth also. Okay, Suppose this depth is h. Okay. Now we have base and radius. Okay. Okay. So if I apply sine c, sine c in this triangle OPA, what will be the value? It will r by this angle, this length AP. It is OA, which is perpendicular, divided by the hypotenuse, which is AP. Okay. Now sine C is equals to OA is R and AP is known to us. So it is AP. Okay. So this, from here you can say this AP is nothing but R over sine C. And this is R over, what is the value of sine C? Sine C is 1 upon mu. So this AP is, mu times R, mu times the radius of the circle. Okay. Just a second. Give me just 10 seconds. So here we are. I'm encountering some technical issue in my this presentation. So that is why I have to switch my camera off and microphone off. Okay. So no problem. We have these two value, equation number 2 we have, and equation number 1 we have. Now in triangle OPA again, if you apply tan C, what is the value of tan C? It is sin C by cos C. Okay. Now, what is tan C? In triangle OPA, it is perpendicular over base. Perpendicular is R, base is H. Sin C, we have known the value of sin C. I can write it as cos C under root 1 minus sin square C from the identity, trigonometrical identity, sin square theta plus cos square theta is equals to 1. Okay. If I just put the value r is equals to, just cross multiply it, r is equals to h times, put the value of sin C. Sin C is 1 upon mu. And it is square root of 1 minus 1 upon mu ka square. Okay. So if you've done all of this calculation, what will you have in your hand? Yeah. So I'm solving it here. The final calculation. Final step, I am writing it. Final step. Okay. So this r is equals to h times mu square root of mu square minus 1 by mu square. This mu square come out from this square root and will become mu, and this cancel this mu. So r here is nothing but h over square root of mu square minus 1. So this is the radius of the circle of illuminance you have. Okay. So if you hand it out, you can ask. Okay. Now the next topic that we have, application of mirage, is TIR. The application of TIR, sorry, application of total internal reflection. So it is first application that would appear to you is as a mirage. Okay. You all have heard about it. What is a mirage? Okay. In hotter palace, like in the Sahara Desert, if you say, so this place is hot. So what would happen? the passengers and the travelers goes there, they would see that it's the inverted image of water and inverted image of the other objects, far distance object. So how this phenomena is taking place? Now what happen is, in the hotter palace, okay, and hot summer day also, the air just above the uh, earth surface will get heated up, density decreases, okay. Whenever the air heats up, heat increase, so density would decrease for air. Okay. So what we have, just above the surface, just above the surface of the earth, we have a hotter section of air, and this hotness is continuously decreasing. So we have layer by layer, hot layers of air. Okay. And a distance far away from the earth, okay, we have colder air. So what is happening? We have two medium here. One is denser, one is rare. So if there is an object which is tall like this tree over here, this tree. Just I will just change the color of the ink. Yeah, this tree you can consider as a tall object. Okay. What is happening? This tree, the ray is coming in this direction. Okay. If I consider the ray diagram over here, the ray is coming in this direction. But there is a boundary we have, because this cold air is dense, denser, and this hot air is rare. Okay. So the application of TIR can take place here. Phenomena of TIR can take place here, because if this ray going to refract, it moves away from the normal, and for a particular angle of incidence, which is nothing but critical angle, it will moves along the boundary, and for the angle greater than theta c, it is moving in this direction. So for you as an observer, the rays appears to from this place. If I just draw the diagram over here, this is the incident ray and it is getting completely TIR. So you as an observer here, you will feel the rays coming from this place. So that why you have a inverted image of whatever the object is here. And this phenomena is termed as the mirage. ठीक है, हिंदी में से बोलते हैं मरीचिका. Okay. So this is the mirage. This is a concept behind it. Do not learn about the fact only. Learn the concept of it. Okay. Now, the next application of this TIR is the diamond we have. So for diamond, the material for which the diamond has to be made. Okay. So for diamond material, the angle of critical is 24 degrees. Okay. Okay. And this is a very less angle. Okay. So what happens, where this diamond is the denser medium and the air is rare medium, so angle of critical is very low for it. So by layer in the diamond, the phenomena of TIR taking place. Okay. And this TIR would cause the brilliant sparkling in the diamond, as you can see here. Okay. Got it? So you can see this diamond, which is very costly also. So see how this is sparkling. This is sparkling because of the phenomena of TIR. If you specifically cut the diamond in a sophisticated manner, so you would have more TIR. Okay. The next topic that we have for the application of TIR is the optical fiber, which is, I have assumed that you have some knowledge of it. You have heard about it, like somehow. You have heard the like geofiber, okay, which is also the working on the optical fiber basis. So what is an optical fiber? Optical fiber is the medium of transmission. Okay, how we are getting signal, we are using internet, how the electromagnetic rays are coming and we are receiving the signal. It is just because of the optical fiber. So optical fiber is nothing but a transmission medium in which the light signal is traveled without loss of the energy. So much loss of the energy, ऐसा नहीं कि there is no loss occur. There is loss, but it is very less. Okay, so what is happening, what is the concept behind the optical fiber is, we have two layer in the optical fiber. Just a second. Yeah, so we have two layer. It consists of core and clad. This is cladding and this is core, and this outer side is the buffer coating, you can see. Okay, it is the plastic covering just for the protection of the this optical fiber. So what is happen here, the light incidence on this core has a refractive index of mu1, this cladding has a refractive index of mu2. Okay, so what is this mu1, this mu1 is greater than mu2, means core is much denser than the cladding. So if a ray is going this, if I set a particular angle of incidence here, okay, this angle is greater than, this angle theta is greater than the angle of critical angle of incidence. So what just happened, this ray do not go in this medium, it get completely reflected. Again the TIR will place here, again here, again. So this signal moves without any disruption of energy to the much higher altitude or much higher length. So this is the application of TIR. Okay, that's how we are getting signal. Okay, in your tower, in your area, you received the electromagnetic rays. These electromagnetic rays converted into a light signal, which is transferred, by the optical fibers. Okay, and that is why we are able to receive that signal. Got it? For this, what should be the maximum value of angle of incidence? So it would be decided by this formula. I max is equals to sine inverse square root of mu1 square minus mu2 square. Okay, where mu1 is the refractive index of medium, refractive index of core. Okay, mu1 here is for core and mu2 for clad. Okay, so this is it. And mu node is the outer medium. Okay, this is the mu node, outer from the optical fiber. Okay, so this is it. We have talked about it. So this is what we have to discuss till now, the application of TIR. So this is it from my side. If you have any kind of doubt in this discussion, in any slide, in any concept, you can just write it in the chat box. Okay, got it. So guys, thank you so much for attending this lecture. Now I will stop presenting my screen. Okay, so